Welcome to Physical Sciences Consultorium. This video is part of the series How We Know the Universe. In this episode, we examine why uncertainty exists in astronomy, what forms it takes, and how astronomers work with it in practice. Astronomy studies objects that are distant, unreachable, and uncontrollable. We cannot manipulate stars or galaxies. We cannot repeat cosmic events at will. All information must be inferred from signals that reach us naturally. Most astronomical signals are extremely weak. Photons arrive sparsely, particles are rare, gravitational effects are subtle. Limited signal strength is the first source of uncertainty. Distance reduces both signal intensity and detail. As distance increases, small variations become harder to distinguish from noise. The farther the object, the larger the uncertainty in its measured properties. Signals do not travel through empty space. Dust, gas, magnetic fields, and radiation alter signals before they reach detectors. Some information is distorted, some is absorbed, some is scattered. Detectors are physical systems. They have finite sensitivity, finite resolution, finite response time. Every measurement reflects both the signal and the detector's limits. Astronomical signals are embedded in background activity. This includes cosmic background radiation, instrumental noise, environmental fluctuations. Noise is unavoidable and contributes directly to uncertainty. Because of these causes, uncertainty appears in different forms, not as a single quantity. Understanding the type of uncertainty is essential to handling it correctly. Some uncertainty arises from random fluctuations. Photon arrival times vary. Electronic noise fluctuates. These variations change from measurement to measurement. Random uncertainty is reduced through repetition. By observing longer or multiple times, random fluctuations average out. Persistent patterns remain. Some uncertainty is not random. It comes from calibration offsets, instrument bias, modeling assumptions. These effects shift measurements in a consistent direction. Systematic uncertainty is addressed by calibration, cross-checking instruments, comparing independent methods. It cannot be averaged away. It must be identified and corrected. Many quantities are not measured directly. They are inferred using physical models. Uncertainty arises from the assumptions built into those models. Astronomers test models against multiple observations. A model survives only if it works across different conditions and datasets. Model uncertainty shrinks as constraints accumulate. Some uncertainty is unavoidable. It arises from finite resolution, finite signal speed, cosmic variance. No improvement in technology can remove these limits completely. Because uncertainty cannot be eliminated, it is measured explicitly. Ranges and error bounds communicate what the data can support. They prevent overinterpretation. A single value hides uncertainty. A range reveals structure. It shows how tightly a quantity is constrained and where flexibility remains. Key quantities are measured using different techniques. Distance, mass, and age are rarely inferred from a single method. Agreement across methods strengthens confidence. Different methods often yield slightly different results. As long as they overlap within uncertainty, they are consistent. This is expected, not problematic. As data improves, uncertainty narrows. Progress in astronomy is measured by constraint, not by eliminating uncertainty entirely. Uncertainty in astronomy comes from distance, weak signals, and physical limits. It is managed through repetition, calibration, cross-checking, and careful modeling. This is how reliable knowledge is built about an unreachable universe. If this way of understanding space science is useful to you, this is exactly what Physical Sciences Consultorium exists for. We focus on how scientific knowledge is built. If you found this episode helpful, Please like, share, and subscribe to the PSC channel.